Rudewright Academy. Learn it, teach it, remember it. A hash table is an array with a formula. The array gives you a box for every number. The formula turns any key, a word, a number, a whole web address into one of those box numbers. So the key itself tells you where it lives, and a lookup becomes a single jump, not a search. Picture the wall of mailboxes in an apartment lobby. You are holding a letter for apartment 11. You do not open box 0, peek inside, close it, and work your way down. You walk straight to box 11 and slide the letter in, one clean motion. The number on the envelope told you exactly where to go because the address is the location. But real keys are not tidy apartment numbers. Suppose the key is the word Priya. There is no brass door labeled Priya. The keys could be anything: usernames, web addresses, enormous numbers. You have a wall of 16 boxes and a key that is a word, so how do you turn that word into a number between 0 and 15? Let me build the simplest, honest machine by hand. Take the word cat. Add up its letters by position in the alphabet. C is 3, A is 1, T is 20, and that sums to 24. But 24 does not fit a 16-box wall, so we take the remainder after dividing by 16, and 24 leaves 8. So cat lives in box 8. That remainder step is the funnel, because a million, a billion, any number at all, the remainder always lands inside the table. Sit with what we just bought. To store a value, you run the recipe and drop it in the box it points to. To find it again, you run the exact same recipe on the same key, get the same box, and read it back. The key always computes to its own address, so store and lookup are both a quick calculation and a single jump with no searching. Here is the crack in the dream. We have 16 boxes and might store thousands of keys, so 2 different keys must eventually want the same box. Watch it happen, because cat sums to 24 and lands in box 8. Now act. 1 plus 3 plus 20 gives the very same 24 and the very same box 8. 2 different keys, 1 slot, and that is a collision, so a hash table is only as good as its plan for handling one. The first cure is almost insultingly simple. Do not store a single value at each slot, store a little list. Each slot becomes the head of a chain, so when a key lands on a slot that is taken, you do not panic, you just add yourself to that slot's list. The slot holds a bucket of everyone who landed there. Let me build one by hand. Insert cat, it hashes to 8 and slot 8's list becomes cat. Insert dog, that hashes to 10 and slot 10 holds dog. Insert act, it hashes to 8 again, but slot 8 already has cat. So we do not panic, we append, and slot 8 is now cat, then act. Insert emu, it hashes to 7, slot 7 holds emu, so collisions did not break anything, they just lengthened a list. Now a lookup. Someone asks for act, so we hash it to 8, jump to slot 8, and find a list of 2. So we walk that little chain comparing keys. Is this cat? No. Is this act? Yes. So we return its value, and that short walk is the only searching we ever do. Deleting is just as gentle. We hash to the slot, walk the chain, snip out the match, and the chain heals around the gap, so keep the chain short and lookup stay fast. The second cure refuses to keep side lists. Every key lives directly in the array, 1 key per box. So when a key collides, it goes hunting for the next open slot and sits there instead, and this is open addressing. Think of a crowded cinema. Your seat is taken, so you shuffle 1 seat down, and if that is taken too, 1 more, until you find an empty seat. Everyone follows the same rule. Work it by hand. Insert cat, box 8 is empty, so it sits. Insert dog, box 10 is empty, it sits. Insert act, box 8 is taken by cat, so we probe forward. Box 9 is empty, and act sits there, 1 door down from where its hash pointed. Insert eel, say it also points to 9, but 9 is taken by act, 10 is taken by dog, and 11 is empty, so eel sits there after hopping past 2. The lookup must replay that same shuffle. Someone asks for act, so we hash to box 8, and that is cat. Not who we want. But we cannot stop, because act may have been bumped forward. So we probe box 9, that is act, found. The rule is, start at the hash box and walk forward until you find the key or hit a truly empty box, because an empty box means it is not here, it would have stopped at the first opening. Open addressing keeps everything in one tidy array, which is cache-friendly. But it has a famous hazard. As the table fills, those forward runs get long and merge into each other, so a cluster of occupied slots makes every nearby key probe through the whole thing. And deletion is fiddly, because if you simply blank a slot, you cut a probe chain in half, and keys past the gap become unfindable. So you mark it with a removed tombstone instead, and the probe passes through and still finds them. Both cures share one truth. A hash table is fast when roomy and slow when packed. We need one number for crowding. It is the load factor, the number of keys divided by the number of slots. 4 keys in 16 slots is 1/4, roomy. 12 is 3/4, getting tight, and 16 is full. And here is the link to speed. Under chaining, the average chain length is exactly the load factor, so keep it small and chain stay short, but let it climb and a lookup becomes a slog. So we make a rule. Never let the load factor cross a line. A common one is around 3/4. The moment an insertion would push us past that line, we do not allow the table to get more crowded. Instead, we make the table bigger. When we grow the table, we double it. But here is the part that trips everyone. You cannot just copy the keys over. Every slot was computed against the old size, and cat landed in slot 8 because we took the remainder against 16. In a table of 32, the remainder is against 32, and cat's number 24 now points to slot 24, not 8. If you copy blindly, the lookup looks in the new slot and never finds it. So we rerun the hash for every key against the new size, and that refiling is called rehashing. Let me do it end-to-end on a tiny table of 4 slots. Insert 5, the remainder against 4 is 1, so slot 1 holds 5. Insert 9, the remainder is 1 again, a collision, so slot 1 chains 5 and 9. Insert 13, the remainder is 1 yet again, so slot 1 is now 3 deep, 3 keys in 4 slots, 3/4 right on the line. Inserting 2 would make it full, so we stop and resize first. We double to 8 and rehash everyone against 8, 5 goes to slot 5, 9 goes to slot 1, 13 goes to slot 5. The long chain breaks apart, 9 sits alone, 5 and 13 share. Now insert 2 into slot 2, alone, and we are back to 1/2, comfortable again, chains short again, because the table healed itself by growing. The same machine written down. To store, you compute the slot, scan its chain, and append. To find, you compute the slot and scan the chain. And to resize, you make a table twice the size, and for every key you recompute its slot against the new length and refile it, never a blind copy. Watch the code drive the very trace we just did, store, then find, then grow, line by line. Now, why is a lookup constant time on average? A lookup is 2 steps. Step 1, hash the key to a slot, a fixed amount of work that does not grow as the table grows. Step 2, scan that slot's chain whose length is the load factor. And we hold the load factor below a fixed line by resizing, so even as the number of keys explodes, the scan stays a small fixed length. A fixed hash plus a capped scan is a fixed cost, and the resizing is what buys the constant time, but is not resizing itself expensive. Yes, rehashing the whole table is a big operation, but it happens rarely because each doubling buys roughly as many cheap inserts as the table already holds before the next one. Spread the cost of those rare spikes across the flood of cheap inserts between them, and the average cost per insert is still constant, so once in a while you pay a lot, but so rarely it averages out cheap. Now the honest caveat. The worst case is linear, as slow as scanning a plain list, and it happens when the hash sends everyone to the same slot. An attacker who knows your recipe can feed keys crafted to all land on slot 8, so that one chain holds every key while the rest sit empty and a lookup degenerates into a long walk. That is a real denial of service. The defenses are a good hash that scatters keys evenly, a secret random seed so an attacker cannot predict collisions, and a tree fallback inside an overlong chain so even a worst bucket is searched in logarithmic time. So hold the two cures side by side. Separate chaining is forgiving, a collision just lengthens a list, it can hold more keys than slots, and deletion is a clean snip so it tolerates a fuller table. Open addressing is lean and cache-friendly, one tidy array, but it suffers clustering, needs tombstones to delete, and falls off a cliff as it nears full. The one-line chaining is robust under pressure, while open addressing is faster with slack but fragile when crowded. How do you spot a hash table in the wild? Ask, am I about to repeatedly check, have I seen this before, or what value goes with this key? Do I need lookup by an arbitrary key, not by position? Do I not care about order or ranges because if I do need order, I should reach for a tree instead? Am I counting or grouping by a key because if yes, it is a hash table? The deepest tell, whenever a brute force solution is a nested loop searching for matches, a hash table usually collapses the inner loop to a single lookup, turning quadratic work into linear, and it shows up everywhere. A dictionary maps a key to a value, the core use. A set remembers what it has already seen, so duplicates gray out. Word count drops each word into a bucket and ticks a tally. Group by sorts mixed items into buckets by their key, so anything that maps a key to a tally or a bucket is a hash table wearing a costume. A handful of mistakes cause most hash table grief, and the first is a bad hash that clumps keys into a few slots, so scatter them evenly instead. Second, letting the load factor climb without resizing, so enforce the threshold. Third, resizing without rehashing, so rerun the hash against the new size, never copy slots. Fourth, a key that changes after it is stored, because keys must stay stable. And fifth, blanking a slot to delete under open addressing, so tombstone it instead, and the universal fix is to hash a few keys by hand and look at where they actually landed. So here is the whole machine once more. A key flows through the formula, jumps to its slot, a collision chains, the load factor climbs to the line, the table doubles and refiles everyone, the chains scatter short again, and a lookup is a jump and a short scan. That is it. A hash table is an array with a formula. Compute the slot. Cure the collision. Watch the load factor, constant time on average. Linear only when a bad hash sends everyone to one slot. Want to keep learning? Come find us at academy.rudewrite.com.